The notion of feeling force is a very prevalent one in physics. Velocity is subjective, we are told, but acceleration is real because matter feels force. But what does it mean to actually feel a force? Is it something that applies only to people and conscious observers, or is it experienced by all substance in the universe? Indeed, the vagueness of the word feel begs the question: is the idea of feeling force even accurate, or is how we understand one of the most central concepts in physics fundamentally wrong? This is Dialect with Can You Feel Force? If you're studying physics, it won't be long before you come across a statement that goes something like this. As an observer, you won't be able to tell if you're moving at a constant speed or not, but you can tell whether you're accelerating, because you can feel a force. This statement is in reference to scenarios such as being in a windowless train or car and not being able to tell what speed you're going, but being able to feel acceleration or deacceleration as you're pushed or pulled about your seat. It makes sense in an everyday context because we as living organisms can feel certain forces, most prominently through our sense of weight, which is a register of the normal force of the earth and other materials pushing against us. But this statement is also used to justify why acceleration is a privileged state of motion, not just for conscious observers, but for all matter and content in the universe. So, if you're an astute thinker, such a statement will seriously make you scratch your head. You might wonder what exactly is meant by the word feel, since it is a biological term that applies to the sensory functions of living organisms. After all, forces aren't just experienced by people, but by every type of physical object in the universe. And indeed, if we ask how precisely the presence of a force is felt or discerned, we are going to come across some major issues. Even if we rule out the most literal interpretation of feeling force, that is, via nervous systems and all that, an ambiguity in the concept still remains. An ambiguity which, as it turns out, is not just a reflection of our poor choice in terminology, but rather a reflection of our fundamental ignorance of the nature of force itself. The problem is this: force is not an observable. It is not something you can directly measure, like a time interval or a spatial displacement. It is a hypothetical construct that takes two measurable empirical quantities, mass and acceleration, and associates them via a mathematical framework. That means while we can directly see things like acceleration and motion, we can never see force. Rather, we can only deduce its presence by applying Newton's laws. This is an important point, so let's make sure to clarify it. Consider that you're on a train at a train station, with another train on the next platform over. Suddenly, your train begins to move. If, like many modern trains, it accelerates smoothly enough, you might become confused about whether it is your train or the adjacent train that is in motion. This is a sensation that, if you travel a lot, you'll definitely have experienced before, and it's one that can be pretty perplexing because it thwarts our typical understanding of reality. It's a sensation that tells us acceleration isn't always felt. And if you've experienced it, you'll know that what resolves it is observation of the surrounding environment. This is because once you see that the loading platform or the station terminal is also moving away from you, you are much more confident in your ability to say that it is your train which is truly accelerating, and thus deduce that there is a force acting on you. That's the key point. You must deduce where and how a force is acting. You never measure it. Force is realized only through knowledge and inference. This makes it an epistemic phenomenon as opposed to an ontological one. Let's take another example. You're in a vehicle with an accelerometer. When you see the accelerometer move, you can conclude that the entire vehicle, and thus yourself, is experiencing a force. You might be tempted to think this use of an accelerometer constitutes an objective measurement of experiencing a force, but this is not the case. Consider instead that you're now in an empty room with that same accelerometer, and again you see it move. Being that you don't think it's probable the entire building is experiencing a force, you are more likely to conclude there's a magnet beyond the wall or some internal mechanism of motion in your accelerometer that is causing its sudden movement. These considerations point to the conclusion that force is a context-dependent phenomenon. You're already probably familiar with this idea through centrifugal forces, or any other quote-unquote fake forces which are coordinate-dependent. But that's the subtle distinction that's left out when real forces are discussed. All forces are initially coordinate-dependent. What makes a force real or absolute is determined after the fact via global considerations. We can make this idea more precise. Consider an object that accelerates relative to you. You can apply Newton's laws to determine that it is experiencing a force. But here's the catch. Newton's laws are only valid if you are certain your frame is inertial. Otherwise, it could be you who is accelerating, rendering the force acting on the object a false coordinative one. Thus, explicating a force requires two components. 1. Observation of a material's acceleration, and 2. Knowledge that your observer frame is inertial. But how do you know that your observer frame is inertial? That's the tricky part, because there's no real prescription for determining the inertialness of a frame. An inertial frame is defined by the absence of external forces, but to ensure you aren't experiencing external force means measuring for forces around you. But measuring force first requires knowledge that your frame is inertial, which requires measuring for forces.
Oh no, vicious circle alert.
Okay, obviously that won't work. Well, there's a second, less precise method, which is just observing the majority of matter and energy around you and making sure you're not accelerating relative to that. For example, when you spin in a circle, all the stars and universe spin relative to you. That's a pretty good sign that your frame is not an inertial one, and that the centrifugal forces pulling your limbs outwards aren't real. Thus, to be confident of the presence of a force requires multiple observations, not just of whatever matter is experiencing the acceleration, but also of the surrounding environment and its behavior. This is what so many people get wrong about force. They're taught to couple it blindly to acceleration, when in fact these are two vastly different phenomena. Acceleration is measurable and always relative to the observer, while force, which hinges on one's knowledge of the total system, is epistemic and inferred indirectly. This means you can never feel force, not in any sense of the word. Indeed, the more you examine force, the less tangible it becomes. Not only does the reality of it differ widely based on context, but one entire fundamental force, gravity, was shown by Einstein to be something else altogether, an emergent property of the geometry of spacetime. Quantum mechanics, meanwhile, doesn't even bother with the concept of force. But even before modern physics, the ontological status of force was already well being called into question. Philosophers and physicists, the likes of Lazare Carnot, Gustav Kirchhoff, Henri Poincaré, and others, were so bothered by the unobservable unreality of force that they all independently attempted to construct a framework for classical mechanics that did not invoke the concept of force, but rather relied on observables alone. What bothered Poincaré in particular was the idea of associating force with causation. As Charles Platrier wrote in Rational Mechanics, force is only a human concept, and we have no knowledge of the profound causes of motion. It's as though force is most truthfully a stand-in for what we don't understand about the nature of change. Moreover, the inability to define it locally means that statements like the one from the beginning of our video, which assert the local distinguishability of accelerated frames, aren't necessarily correct. That means if force and change are truly connected, reality might not be as objective as our intuition tells us. After all, there is no way of truly feeling force. This has been Dialect. Thanks for watching.